Hi, everybody. Hope you're doing well. As you can see here, I'm riding on a drone, I guess. It's kind of a nice scene. There's a lot of movement. If you get seasick or airsick, let me know and I'll put another background on, but it's kind of cool. Looks like it might be in Switzerland even. Okay, hope you're doing well. Let's see, any announcements or anything like that? Nope. I guess you all have seen your grades, and if you have any questions about the grades, please do see your TA first, and they'll go through the tests with you. And then if you have any questions after that, I'm happy to meet with you as well. But I guess that's pretty much it. Let me just, okay, I realize I just froze for a second. I think I'm back on now. Let's see. Oh, happy Diwali. Thank you. Very nice. All right. Okay, not quite sure what the comments are about. But okay, anyway, so let's go ahead and get right into our lecture for today. We've been continuing our discussion on visual perception after kind of establishing all the theories that will be relevant to what we'll be discussing for the rest of the quarter. And we are addressing now the issue of distance perception or depth perception. And what I'm going to do today is talk about some very classic research and then supplement it with some very recent research and talk about the issue, to address the issue of what the primacy of the different types of visual dimensions are for distance perception, as we were discussing last class. Remember, we talked about the possibility that you can portray the different types of input as cues versus information, and that's kind of associating these different dimensions with kind of the theoretical emphasis of a more computational information processing sort of approach versus Gibson's approach, where Gibson suggested that the sorts of dimensions that one could rely upon were probably the ones that were primary, where an information processing approach would probably predict something a little different. And we'll talk about that in some detail after we first establish how we're going to test infants on these different types of dimensions. So let's talk about some of the classic studies. Oh, thank you for the enabling of you enabled my transcription button. Thank you. Okay, just a second. This is where we left off last time. Share screen, please. Okay. So we were talking about the different visual dimensions usable for depth and distance perception. And we left off with this kind of fun one having to do with demonstrations of audio stereograms and these kind of cool things, and talked about the that there is some of the population that does have trouble with these, and that's okay. There's nothing to worry about if you weren't able to get them. Most people are, so it's really kind of an issue of kind of sitting down and trying to do the unfocusing of your eyes and kind of focusing on something behind your screen. But there still is 5% of the population, and that is based on the misalignment of the axes of your eyes. So here are the eyes looking down now. So this is looking forward, this is down. And it's just really that they turn it in a very subtly different way like this. And in doing so, it kind of prevents this fusion that you can use to get these audio stereograms. But even with that 5% of the population, these folks are typically able to, use some sort of stereopsis, even if it's not perfect. They might not be able to use these 3D glasses at the movies and that sort of thing. But the fact that the brain is getting two different images probably is helping to some degree, even if they don't have a terrific integration. But it's just an issue of poor binocular coordination. These people still have the ability to perceive depth. They're using other types of dimensions, obviously. But there's nothing to worry about if you can't do these sorts of images. Okay, now let's start talking about the new stuff. And that's going to have to do with the question about whether depth perception is innate. Now, as we've already kind of flagged, there's lots of issues with using the term innate, right? We use that in the context of the Gestalt approach, and it really meant something very different to them. But even just, methodologically, it's difficult to really establish these sorts of things. And so we're going to use the term very loosely here. Just as we mean it here, we can talk about the question more as, does it seem that infants have the ability to perceive depth and distance at a very early age? Without making any assumptions that they have the ability as soon as they're born to do so, right? That's what innate would more formally mean. And let's talk a little bit about the history of this sort of work, both with human infants and animal infants. So we're going to go way back, older than me even, to 1960. And some classic experiments that were conducted by Gibson and Walk back at that time, having to do with an apparatus that you probably learned about before in other classes, your developmental class, your introductory class, called the visual cliff. And these were babies that were tested that could crawl. Yeah, I should mention that back then, just as a quick aside, babies could crawl typically earlier and would spend more time crawling. And that's partly related to the fact that these days, I certainly did this with my kid, all babies are put on their back to sleep because that seems to be the safer sort of orientation for them to be in. The problem with that is, since they spend so much time on their back, they don't crawl as often. So neither of my kids crawled very much. They kind of went from kind of wiggling around to pretty much standing, and maybe there was a month or two where they were crawling around, but not a whole lot. And that's not uncommon these days. Back then, kids were doing a lot more crawling. So you could get kids to crawl between 6 and 14-month-old, and you'd put them on this apparatus called the visual cliff. And the idea was, could they kind of traverse the cliff? Could they crawl across the cliff? And in so doing, show what they were perceiving as depth. Okay, so I think you can probably see this from here. There is kind of a plank on the middle of this big table. It's a very large table, probably the size of a huge banquet table, say. There's a plank that goes to the middle that the child is put upon right here. And then there are two sides to this table. One side has kind of a shallow surface, and the other side has a deep surface. Okay, so this would be the shallow surface over here, and this is the deep surface over here. And I should mention right off the bat that there actually is a pane of glass over the entire thing, so the kid cannot fall off and hurt himself. That being said, the glass is cleaned completely, and the lighting in the room is situated so the glass isn't really reflective. In other words, it's hard to see this glass from the perspective of the infant. They really try to make it as transparent as possible, very few reflections from the infant's angle. So, from the infant looking across the table on this side, or the shallow side here, or the deep side here, they're pretty much not going to see the glass, right? They're not going to realize the glass is there until maybe they touch it or something like that. And then you put the mom either on the shallow side or the deep side. And here you can see she's now on the deep side. And you ask the infant to go to the mom. The mom kind of coaxes the infant to come towards her. And the question is, will the infant at this age feel comfortable going on the deep side? And so here you can see the infant readily goes to the mom when it's shallow, but when it's deep, the infant is really apprehensive about this. And so potentially this might suggest something about, at least at this age, which is, that's a lot of visual experience at 6 months, but this is how it was initially tested. It seems that the infant is, sensitive to differences in depth, which maybe isn't too surprising. at that age. We'll get into other sorts of methods that are used for younger babies in just a second. But it's interesting that this type of kind of simple methodology can at least tell you that much, which is interesting. Yes, the baby has to be old enough to crawl, and the baby does have visual experience by that point. But it does tell you something. At least by the age of 6 months, the infant seems sensitive to the deep end versus the shallow end. Okay, there's other things we're going to be able to do to manipulate certain things to find out different sorts of kind of processes that the baby is using to do this. But I kind of wanted to establish this right off the bat. Now, one other thing I wanted to mention, because it is something they noticed right away, which I think is interesting, and it kind of goes back to something we've talked about before, is that the infants would know the glass was there through touch very quickly. So you can almost see this here. No, I guess not. No, oh yeah, no, it's in the next image here. Yeah, there you go. There it is. That's showing it from the other side. And the infant is shown there touching the glass. But even though they are touching the glass and have a sense that this is a solid material that's below their hand, and maybe even could support their weight, that exploration by touch, that I'll call that a touch test, does not make them feel more comfortable moving towards their mom. And I think that's an interesting kind of finding. It suggests here that at least in this situation, vision seems to be primary over touch when it comes to determining something about depth, right? So the infant is touching the glass and potentially could say to itself, well, okay, it's a see-through material here, and probably by the time they're 6 months, they have a little experience with glass, but they're still not trusting it. What they're trusting is their vision to make the determination whether it's something that they can crawl over, okay? Which I think is interesting, because remember what Locke said, John Locke, when we were discussing how vision is kind of educated, right? He said there was kind of a primacy of touch, right? That touch was the thing that kind of the infant had some early ability to interpret. Hopefully for Locke, it was something they learned too, but certainly it was online. It was available to the infant sooner than vision was. And in order to learn those visual cues, the infant had to use their touch experience to kind of educate those visual cues, right? So, to know that this hand is in front of this hand, or an object, a stuffed animal is in front of another stuffed animal, the infant has to kind of reach out and say, okay, this one's closer, this one's further away, but now I don't need to reach anymore, because now I can learn to interpret the cues through association, that this object is covering up this object, gets superposed or interposed over the other object, right? And so we talked about that as kind of a kind of quintessential example of how touch could educate vision, where touch was primary. But here we have a situation where it looks like maybe it could be that touch did educate vision for this infant, but very soon, and maybe a little surprisingly from Locke's perspective, vision is more important than touch. It overrides touch, so that the infant, even though they're feeling a solid surface, will not go over that surface towards their mom, because there's not this visual information for a shallow surface. It's a visual information for a very deep cliff that they could topple over and get hurt on potentially. That is telling their visual system, nah, this isn't safe, despite their touch system saying it is safe. So it's kind of troublesome from Locke's perspective. Okay. Anyway, so clearly, infants have a lot of visual experience by now, 6 months, 14 months. They're crawling around, they're touching a lot of things, they're seeing a lot of things. Are there other ways of testing this? Of course, in the visual cliff, the infant has to have these abilities in order to test these sorts of things. So what Gibson and Locke did fairly quickly afterwards is they decided to test other animals. And the interesting thing about other animals, you might know this if you worked on a farm or have any experience in owning farm animals, that, oops, in fact, there are lots of animals that can start locomoting on their first day of life. It's interesting that there's all these kind of theories about why humans take so long to be able to move, walk, and stand. So why they take so long, where other animals like chicks and baby goats and horses and cows stand on their first day of life, which is pretty amazing. So there's lots of reasons having to do with the baby size and all that sort of stuff I won't get into now. But what this allows those researchers to do is actually look more closely at the possibility, using their same method, the visual cliff, that depth perception is available at the first day of life. Okay. And there's been some controversy over the findings here, but I think for the most part, we can say this, that at a half day old, a baby goat, like this cute one right here, if put on the shallow side of the cliff, is perfectly fine. But boy, you put this poor little baby goat on the deep side and they freeze. They absolutely freeze. They do not move, or if they do move, they look around and try to jump to the shallow side as quickly as possible. It's like the goat is all of a sudden saying, oh my gosh, I'm floating and this does not feel right. I don't feel like there's a ground beneath my feet. And they take this kind of very kind of characteristic defensive posture. When young animals get scared, they go into this posture. They, as I said, they kind of freeze, and they'll jump to the other side at some point. And so what this suggests, at least at a half day old, these baby goats and the chicks that were also tested, they seem to show a sensitivity to depth, again, using this very simple visual cliff methodology. So, at least based on these findings, it suggests that animals, maybe not humans, but animals do have sensitivity to depth, to distance at a very, very young age, a half day old. Okay. All right, cool. So what else can we do with this visual cliff? And this kind of gets interesting. You think, well, it's kind of a cool apparatus, but how many experiments, how many different questions can we address with this? You'd be surprised at how much is done with this sort of thing. And people still use the visual cliff, although it's a little different these days, but I've seen some more recent ones. But this is really quite a very useful sort of method for understanding infants and perception and motor coordination. So here's what you can do. Oh, yeah, there it is. There's that little baby goat jumping to the safe side. There he goes. All right. What you can start doing, at least on a first pass, is to start looking at the relative importance of different visual dimensions for perceiving depth when it comes to how an infant uses this information. Okay, so let's talk a little bit about how this might kind of play out. Let's think about two different types of visual dimensions we've talked about the last class, and a few times throughout the quarter for that matter. We'll use the relative size and motion parallax dimensions. Now let's just remind ourselves of what this is. Relative size is the type of visual dimension for distance perception that suggests that the bigger an image is as it's detected by the eye, the closer it would appear to be. And so you can look at these little puppy dogs here, if I asked you, if I asked you what the relative distance is of each of these dogs, you say, okay, I see what the image is trying to do. It's 1 is a close puppy dog, and 6 is a far puppy dog, and there's all these in between. So 1 is closer to 2, 2 is closer to 3, that sort of thing. And that's the relative size cue. I mean, it's something that's been used in art for a very long time, longer than linear perspective has, before the Renaissance. Okay, makes sense. The other type of visual dimension we're going to talk about is the motion parallax one. And that's just the idea that when you're moving forward, remember, you can think of yourself on a train or looking out the side of a car, or just do this, that when you move forward, the distance of something will determine how quickly its image kind of flows across your retina, right? So I'm moving forward and my left finger, can you see these things? Yeah, okay, my left finger is closer and you can kind of get an introspective sense of this. The left finger seems to move across my eyes faster than my right finger. Okay, this is something we talked about before. So the question is, when it comes to an infant, which is the more important sort of visual dimension? One other thing I can say about these, and this should sound familiar, that I portrayed the relative size dimension as a cue because it's not always available and things can be different sizes and that can kind of offset the distance and that sort of thing. Where motion parallax, for the most part, is much more reliable. It's much more trustworthy, and it seems to be kind of based on a lawful relationship between our motion and the distance of things in the world and how those things images kind of flow across our eyes. Okay, so I have been portraying relative size as a cue and motion parallax as a type of information. Okay, but now let's think about the infant's brain and how it might be able to use these two types of dimensions. Oh shoot. Hold on just a second. Let me, hold on a second. Okay. Okay, I put this in the wrong place. Hold on, I'm gonna do this. Hold on just a second. I wanted to add this phrase here. No one panic. Everyone's going to be very happy as soon as I do this, because I'm going to actually change. Yeah, okay. Yeah. Okay. All right, sorry about that, everybody. I had to add a term. And it's not going to be consistent in your, you'll see in the slides, it's going to go off and come back in. But here's the issue. I think this is an important term that I added today. It has to do with the processing complexity, right? So if you're an infant and your infant brain is just developing, the question is, are you going to be better with simple types of input or complex types of input? So let's talk about relative size and motion parallax as simple versus complex. So what happens with relative size? Okay. Oops. Okay, sorry about that. Well, with a pictorial cue like relative size, what you have there is a single image that acts as the input, right? It's something that can be, as I said, captured in art, right? It can be captured in a photograph. So the processing complexity of that isn't much. A single image comes in, and the infant's brain, since it's supposedly learning to interpret all these things and doing things a little bit at a time, is going to have a relatively easy time with that type of input. Where potentially, when it comes to the assumed processing complexity of motion parallax, things might seem at least a little more complicated. In order for motion parallax to be usable, assuming, and this is now an assumption I'm making kind of from a computational perspective, an information processing perspective, that motion parallax has to be kind of calculated over multiple images, right? Remember the information processing kind of computational perspective suggested that the input for vision was, kind of more pictorial. It was more like photographs. And if that's the case, in order for the brain to use motion parallax, then it's going to have to kind of compare this input to that input, right? Or, maybe this input to that input to that input as I'm moving my head forward. It's going to have to process multiple images and then integrate those images in order to, use motion parallax. So as I'm portraying it here, and this is kind of a portrayal from a computational perspective, an information sort of perspective, it might seem that the pictorial cues would be easier to calculate, easier to process for an infant, okay? Because it's just like a snapshot, single snapshot, let's see what's bigger, versus motion parallax, where potentially you've got to take a sample here, or maybe a snapshot here, and as I move forward, then a sample here, and then another sample there, where there has to be an integration, kind of a comparison, maybe instead of integration here, we can use the word comparison, between each of these different kind of snapshots of the world. So it would seem that for an infant, the pictorial cues would be simpler to process. Okay, they'd be simpler to process, and therefore potentially primary. Okay. So again, I blew this slide. I apologize. I'll fix it when I post it. This said something here about processing complexity, and in fact, it seems that pictorial cues have a simpler processing than the motion parallax, because again, it's a single image for pictorial cues. Well, for motion parallax, if we're assuming that it is kind of like a photograph that's our image, that is our stimulus, it has much more that needs to be done. So when it comes to predict what the infant will rely upon most, a pictorial image, or something like motion parallax, is it relative size, the pictorial cue, or motion parallax? You might think from a computational perspective, well, again, you get a single snapshot, that's a much easier processing task than what's needed for motion parallax. So you make the prediction that pictorial cues are simpler and primary. Okay, let's just kind of leave that now and now test it, just simply using the visual cliff. So, okay, let me show you what I'm trying to do here is introduce you to a lot of things at one time, not just the developmental kind of methods that are used, but a developmental method that's very straightforward. I mean, you can set this up at home if you have an infant to play with, right? This visual cliff thing is not too hard to set up, but you can actually address this kind of deep question that's kind of going to help you kind of determine whether this idea of simplicity in the input is what the infant is going to rely upon, right? That's kind of a big question with a very straightforward, very simple kind of method that can be tested. So here's the method. Here's how you do it. So what you can do is, after you set up your visual cliff, is that you can manipulate the size of the squares. So let's quickly kind of just think about what the visual cliff looked like on the previous slides, right? It was basically checkerboard, I don't know, wallpaper or checkerboard. I've bought this stuff before for experiments. You know what they use it for? It's like to line drawers with, checkerboard drawer lining. So, if that's what you like, that's your style at home, you can kind of line your silverware drawers with the checkerboard patterns. Now, the cool thing about the checkerboard patterns is not only are they very simple and they're very visible, right? But you can actually get them in different sizes. So what you saw in the previous images was were checkerboards of all the same size, right? All the checkerboard wallpaper was all the same size. But here, what you can do is manipulate the size. You can go out to your hardware store and buy checkerboard wallpaper that has different size squares. And you therefore can manipulate the size of the squares at different positions in the visual cliff. All right, so for example, you can simulate depth with the square size. And this is a little tricky to see here. But what you're basically going to do is on the shallow end of the visual cliff, the shallow surface of the visual cliff, you're going to use the wallpaper that has smaller squares. So from the perspective of the infant on the plank, The square size at its eye is the same on the shallow side and the deep side. Okay, let me just go back to these. There you go. And maybe let's use this. No, let's use the goats. So in other words, what you're doing here is you're going to, as you can see here, the squares from the goat's perspective, the actual absolute size of the squares that are hitting the goat's eye are smaller, right? Relative size. It's smaller because it's further away, okay? And smaller than what's at the shallow side over here. But as I said, what you can do is you can simulate depth here potentially by making these squares smaller. So the squares at the goat's eye, that's at the plank, that's on the plank, is the same on the shallow side and the deep side. Okay, the square size at the goat's eye is the same because you got small squares on the shallow side that are actually equal in size at the eye to the deep side squares, which are actually a little bit bigger. I'm hoping you get this. Basically, you're trying to portray the sides as equal in depth because the squares at the goat's eye, or the baby's eye, are the same. You're going to kind of simulate depth in that way. All right. So you do that. You simulate depth with square size. And now you see if the infant prefers one over the other. Right. So, it should be if the infant is depending on relative size as a cue, then now they should see both sides as equally deep, right? Because now there's a simulated deep side because you're using smaller squares on the shallow side, and then a real deep side. And if they're just using the relative size of the squares, they shouldn't care. They really shouldn't care. But in fact, okay, it doesn't make a difference. I'm sorry. Wait, hold on just a second. Simulate depth with square size. I'm sorry. Okay. I blew this a tiny bit. So what you're going to do is on both sides. So that's what I just told you is the second part of the experiment. To get it consistent with my slide here, what's written on the slide, we're going to kind of just do one other thing, and we're going to make both sides shallow. Okay, so now we're going to lift up the deep side. So now both sides are shallow, but we're going to simulate depth because one of the shallow sides is going to have small squares, and the other of the shallow side is going to have big squares, right? And you would think that the infant would prefer, if it's just basing its depth perception on square size, it would in fact prefer the one that has the bigger squares, right? Because we're simulating a deep side here with smaller squares. But that's not what happens, okay? When both sides are actually shallow, but we're simulating depth by having one side with smaller squares, infants don't care. It seems that they kind of ignore the size of the squares, and they'll go equally for the deep side, or I'm sorry, the side that has big squares and the side that has small squares that are equally shallow, okay, but are simulating, one of which is simulating depth. So it seems like they're not fooled by this at all, that the square size is not going to be something that's going to fool the infant into thinking that one size is deep and one side is shallow. Okay, so they're not, it seems, using relative size in this case. Okay, now what we're going to do is what I suggested, is you're going to have a deep side and a shallow side. So this one's going deep now, and can I see my hands? And this one's going shallow, but you're going to equalize the squares at the infant's eye. Okay, so on the shallow side, you're going to kind of have small squares. On the deep side, you're going to have big squares. But when it comes to what's going to the infant's eye, in fact, the squares are the same size on both surfaces. Okay, you would think that if, in fact, they were just relying upon relative size of the squares, that since at the infant's eye, it's going to be the same, they're not going to have a preference. But in fact, they do have a preference. They, in fact, are not, again, tricked by the relative square size into thinking, in this case, that both surfaces are equally deep. Instead, they still prefer the shallow side, the real shallow side, even though it has smaller squares and it's simulating depth. In fact, they won't go over the deep side, okay, despite the same size squares. So what it suggests here is, in fact, that infants aren't fooled by relative size as a cue. It is not the primary cue for them, it seems. And in fact, it's thought in these cases, what the infant's doing, and I would love to be able to see a video of this, but these are the reports. What the infant's doing is they are moving their little head an awful lot in these situations. They're kind of looking over the plank that they're on and looking below on both sides as they move back and forth. And that allows them to not be fooled by relative size cues. In fact, what seems to be primary here is motion parallax. So even though from a computational processing perspective, it would seem, at least intuitively, that the simpler the dimension, the simpler the cue, the more primary that would be, the more the infant would rely upon it. That's not the case. What they rely upon is something that might be more complex, right? But is information, and is something that is really very trustworthy in the world, much more so than a pictorial cue. So what they rely upon in this context is, in fact, the type of visual dimension that is more lawfully related, more often available, and more specified when it comes to what's available than what might be easier to process from kind of a computational perspective. They rely upon motion. Okay, they rely upon motion. Okay, let's take our little break here, our first little break, see if there's a question. Are they ignoring depth or size because they don't notice it since they rely more on touch? No. Okay, very, very good question, Alexandra. So Alexandra asks, are they ignoring depth or size because they don't notice it since they rely more on touch? No. In these situations, it's a very good question. In these situations, the infants aren't able to touch it. They put something on the side of the I guess the plank somehow that prevents them from touching it. And it's not like they're ignoring depth, right? They're able to perceive depth, but the question is, on what visual dimension are they able to perceive depth? And it seems like it's not relative size. It is, in fact, another dimension that allows them to perceive depth, which is overriding relative size. And that's probably this motion parallax that they're able to use still, okay? So no, it's a great question, Alexandra, and the experimenters have to make sure that they're not able to use touch. So very good question. Okay. By the way, and as you know already from our previous discussion of this, touch doesn't seem to override the depth that they are perceiving visually, right? They do rely more on visual depth, even though it's not based on relative size. They are relying more on visual depth than on touch depth, right? We talked about that before. It's a good question, though. Okay, so let's go ahead and do one of our polling questions, and I think this will address exactly what we just talked about. Yeah, okay. So the visual cliff experiments discussed in class provide evidence that A, depth perception is acquired through experience. B, depth perception seems available at or relatively near birth, as early as it can be tested. C, infants rely more on motion parallax information than relative size cues. Or D, both B and C. Should be pretty straightforward, and it looks like everyone's doing very well. All right, I'll give you another 15 seconds or so. Cool. All right, great job. So most of you got this correct, and the answer is D. Both B and C are correct answers, so you would mark D on a test. Okay, depth perception is acquired through experience. Well, okay, probably as you're going to see, certain dimensions are, certain visual dimensions might be acquired through experience, which we'll talk about. But the idea of depth perception, at least based on these experiments we've been discussing in class, seems to be something available very early on. And that's, if nothing else, I think nicely demonstrated by the animal studies that after half a day of life, they're able to get on the visual cliff and perform in a way that shows they clearly have a sense of depth, right? They get scared if they're on the deep end of the cliff, despite, having glass under them. So depth perception seems available at or near birth. And then you just learned that infants rely more on motion parallax information than relative size cues when it comes to the relative importance of these visual dimensions. So the correct answer here would be both B and C, so you'd mark D for that. All right, hopefully that's pretty straightforward. Any questions on that? Good. I love these drone shots. I think they're so cool. I was watching a movie last night, not a movie, a scary TV series. It's called Midnight Mass. Spooky. I started watching for Halloween, and I still like being scared. Anyway, there's a number of scenes where they kind of show some, I don't know what it's going to be yet, but it's a spirit kind of hovering over a town and is clearly taken by a drone. The camera work is clearly done with a drone where, you kind of take off from the ground slowly and start kind of floating around and kind of go between houses and stuff. And it's supposed to be really scary. They have scary music, because it's supposed to be some sort of evil spirit or something like that. But I just find it so exhilarating. I just love these drone shots. Now, I don't know about you folks. Do you guys have flying dreams? Do you ever dream that you're flying? I used to have them more when I was a kid, but every once in a while I still have them. I think drone shots kind of really capture the feeling of what it's like to fly in a dream. Okay, this has nothing to do with what I'm talking about in class. I was just thinking about it, looking at this wonderful drone shot, kind of the exhilaration of slowly taking off and then also being able to hover and all that sort of thing. That's what a dream, a flying dream is like for me. I don't know about you folks. Anyone else? Nope, scared of heights. Yeah, some people, Angelica and Jenna, say, yeah, it is like that kind of. Oh, you have to, yeah, Olivia, I've had to do that too. I've had to, flap my arms as a bird or something like that, or, like I'm swimming or something. I've had to do some sort of movement, but boy, those are great dreams. Yeah, flying dreams are amazing. Yeah, Yvette agrees. Cool. All right. Well, enough about my dreams. Let's talk about yours. I'm kidding. All right, let's go back to the lecture. Okay, we're going to continue talking about this, and we're going to actually shift our methodologies a little bit. And again, this is kind of a nice way for you to learn about these developmental methodologies as well as address some of these interesting questions. So we're going to talk about the relative importance of cues and information, but we're going to actually make use of another method, as well as a phenomenon that has been much studied in perceptual psychology, visual perception, both in the infancy context and adult context. And it has to do with the constancies. So I'm just going to talk about one constancy here called size constancy. And it's a very simple notion that if something approaches us, or I'll use my hand because it's one of the few things that this camera, the zoom image thing will pick up. When I perceive my hand coming closer, I don't perceive it as growing in size. My perceptual object here is not a hand that grows; it's a hand that's getting closer, right? And that's true as we move around the world. We don't perceive, even though the flow across the eye is, as we get closer to something, is something that's growing. As a baseball is coming towards us, for example, we don't perceive that the baseball is actually being kind of expanded as it's coming closer, right? It's not like somebody's blowing it up. Someone is, blowing up a beach ball or something like that. The way we perceive it is as being the same size and getting closer. So we perceive a constancy in size despite the image on our eyes changing. And the other constancies that are often discussed are shape constancy, right? So as I move around my hand now, even though the image on my eye, the way this is reflected onto my eye is changing shape, I perceive the shape of my hand as the same, right? That doesn't change despite now that I'm getting a different angle here at all, right? I still perceive the shape is constant. And the other type of constancy that's discussed is brightness constancy. As I can change the lighting a little bit in this room, it's not like all of a sudden all the colors of things change and all the brightnesses of things change. It seems that somehow the brain or the information is allowing us to perceive things as constant. So the question is, how does the brain establish this? How are we able to perceive, especially for size, the things in the world as being a constant size? They aren't expanding and shrinking. Not all the things that are in front of us right now are expanding and shrinking. Very few of them are expanding and shrinking, in fact, and we perceive them as size constant despite the image changing in their sizes. How is that established, and how early is that established? Okay, it's going to be a different method to do this in order to see if infants are able to show size constancy. And what we're going to use young infants here. I'm going to put young infants that I think are between 2 and 15 weeks old. Actually, it can be done earlier, and it has been done earlier now. But what you do is you put a little mannequin head out in front of the infant, smiling. It's a happy mannequin head, so the infant isn't scared of it, and it's life size. And you're going to move that mannequin head closer and further from the infant to determine whether it's perceiving it as the same size. Okay, and the way you basically ask the infant to tell you what it's perceiving is through a very subtle behavior. Basically, what it's going to do is the infant's going to turn its head when it perceives the same thing again and again. Okay, it's called an infant head turning, or kind of head triggering response. And so basically what you're going to do is you're going to operant condition the infant. Remember this from your intro psychology class. You're going to reinforce the infant's response when it responds appropriately. So it's hard to see here, but in the cushions next to the infant's head are kind of little triggers. And so when the infant moves its head either to the right or the left, it sets off a little trigger. And if it does that movement to the right stimulus, okay, you give it a little reinforcement. What's the reinforcement? Okay, so it's a head turning response. There he goes. The infant's making a little head turning response. And if he does it to the right stimulus, then you reinforce it. And infants are easy to amuse. You probably know if you've dealt with them, if you have one yourself, or if you have a little cousin or something like that. All you need to do is go peekaboo, and they love it. So that is in fact what it's called. If you read the papers, it's called the peekaboo reinforcement. And typically it involves either an experimenter or the mom, kind of all of a sudden, maybe jumping up from the side so that the infant can't see the mom, is kind of looking around. Infants love to play peekaboo. And when the infant performs correctly, okay, when they turn their head to the correct stimulus, you jump up from the side and go peekaboo, and the infant thinks it's the funniest thing in the world, right? Good thing that infants are so easily amused, because they will do this for a long time. If you've played peekaboo with a kid, a really young kid, it can last for a long time. But you have to do the experiments relatively quickly, because the infants will ultimately fall asleep if they're in a chair for a long time. So it has to be done within the context of, say, 10 minutes. 5 to 10 minutes are typically how long you get with an infant in this case. But they'll play peekaboo for the entire 5 minutes straight without losing their attention. Okay, so here's what you do. You get them to respond to this situation. So whenever you put the mannequin there, and I think the way they do this, I should mention, is they put like a little curtain in front of the infant here. It doesn't see anything. The curtain lifts, and then they see the mannequin head. And if they see the mannequin head, they do their little head turning response like that, and mom pops up and goes peekaboo and yippee yippee. Now, if the curtain comes up and there's no mannequin head there, okay, they are not to do the little head turning response. And maybe they will. Maybe they think that they're supposed to turn their head initially to whenever the curtain comes up. But if they do it, mom doesn't go peekaboo, right? Mom only does peekaboo when the infant responds with the head turn, okay, clicking off the little sensor there, when the infant sees the little mannequin head, okay? So now you've operantly conditioned the infant to turn its head only when it sees the mannequin head. Cool. Every time the mannequin head is shown, at least initially, in order to establish this operant response, okay, it's shown from this distance, 60 centimeters, right? Then what you do to make sure the infant's always responding, okay, you test it a few more times, right? And it's only responding when the mannequin head's there. Now you do your critical manipulation. What you do is one of two things. Either you show it a half-size mannequin head at a distance that's half that they were trained to, right? Now, so it's a tiny little, it's a shrunken mannequin head. Same type. I mean, you know, it's a smiling little mannequin head. It's, you know, cute. Maybe it's got makeup on or something like a clown. I don't know. They're not scared of it. But now it's half the size, but at also half the distance. And what does this mean when it's at half the size and half the distance? It means that the mannequin head, the image of the mannequin head at their eye is the same as it would be to what they were originally trained for. Okay, that's one of the new situations. The other new situation is this. Okay, so it's an equal, yeah, I should mention that. This is equal retinal size, that this situation provides the same image size to the retina as this situation, okay? You are bringing the mannequin head in closer, but because now it's half the size, okay? In both cases, in this situation, the size of the image of the mannequin head at the infant's retina is the same to the original situation which they were trained to. Okay, that's one of the new ones. The other new condition is this. Oh, fine. Yeah, we'll come back to that in a second. The other new situation is this. You bring in the mannequin head that you originally started with, but you have it at half the distance, okay? So you use the same mannequin head, but now it's half the distance. And in this situation, clearly, the image of the mannequin head is much larger at the infant's eye. So it's unequal retinal size from the original situation, the one the infant was trained to, okay? But let's look at the actual sizes now. In this original case, what you have here is an unequal actual size. The size of the mannequin head has shrunk. Here it has not. It is an equal actual size to the original. So when this says equal retinal size, this is comparing it to the original. When it says unequal actual size, it's comparing it to the original one that the infant was trained to. Same thing here. Unequal retinal size to the original one the infant was trained to, but equal actual size to the one the infant was trained to. And the question is, which of these two scenarios, this new one or this new one, does the infant think is most like the one he was trained to? And so the term for this, by the way, is generalization. Generalization here just means that the infant's going to generalize their response to one of these two situations based on how they were trained. And that generalization, whether they generalize and respond to this one or generalize and respond to this one, is going to tell the researchers something about how the infant is perceiving the situation. Okay, let's go back to our original question. Do infants show size constancy? Can they perceive an object as being the same size despite the change on their eye. This is the situation where the object is the same size despite the size on their eye. This is the situation where the image is the same on their eye, right? But the object has changed. The object's size has changed. Size is constant here. Size is not constant here. What's constant is the size of the image on their eye. And the question is, at 2 weeks old, do infants show size constancy? If they do, if they think that objects that are closer don't change in size, they just are closer, they would generalize to this. And that's exactly what they do. Infants will turn their head when they're shown this situation, but they find this situation very new. It's a half-size head, it's a shrunken head, and they will not respond to this. Infants think this is the same situation or a closer situation to this than they do this. Infants rely on the actual size for their generalization, not the retinal size. Okay, so infants, it seems, do show size constancy by the time they're 2 weeks old. And actually, this has been tested sooner now, I believe. I think they can show this at 1 week, if not earlier. So infants at a very early age do show size constancy. Now let's kind of take a step back and think about what the infant's visual system is like. It's not great at this time. I mean, there's still, things are very fuzzy. They have trouble focusing, right? This is why one of the reasons Locke said, yeah, you gotta teach all these things. An infant, this would be very much kind of contrary to what Locke would say, right? It looks like a very young age, infants have the ability to see constancy, size constancy, despite their vision not being great and despite them not having a lot of experience. Size constancy seems like it's on board pretty early on. Okay, cool. How are they doing this? How are they perceiving size constancy? And now we're going to go back to the kind of bigger question about the relative importance of cues versus information. Now they've shown size constancy. Let's do some manipulation of the different types of visual dimensions. So basically, we're saying, test the distance cues or information for size constancy. And this is another really kind of clever experiment. And this is kind of, this was done quite some time ago, but I think that this is held up even with much more kind of sophisticated methodologies that are used today. Here's how we're going to do it. We're going to run 3 groups of babies. Knowing now that they're all going to show size constancy, let's see what type of dimensions they're going to be able to use for size constancy. So in other words, they're, for size constancy to work, they've got to see the things as closer, right? They've got to know that this is the same size mannequin head as the one they were originally trained to. They've got to know it's closer. The question is, how are they able to do that? What types of visual dimensions do they use to determine these things are closer? And we're going to run 3 groups of babies. One group of babies is actually, we're not going to use the mannequin head anymore. We're going to use 2D pictures, right? That's going to be something like this, right? To test their sense of depth that will allow them to perceive size constancy. That's one group of babies, all right? Another one, lucky for the babies, they get to wear these 3D goggles. And yeah, again, babies at this age, their vision isn't great, but they do have, stereopsis. They are able to see, able to use 2 eyes to perceive something about depth. So there's a baby with 3D goggles. No, I said just a baby with sunglasses, but I'm trying to portray there that it has 3D goggles on. And back then they weren't using the best quality, but this has now been replicated with the type of goggles that we use in the movie theater, which is very effective for most of us. And they make sure the babies are able to fuse, and they're not, they don't have a strabismus of any major strabismus or anything like that. And so yes, babies can use 3D pictures even at a very early age. The final group of babies is kind of interesting. These are going to be babies that are just going to be able to use a single eye. Okay, you'll see how we'll do that in a second, but they're actually not going to see pictures. They're going to see a scene. They're going to actually see a real scene of 2 boxes, one in front of the other. Okay, And how do we do that? We make pirate babies, right? We just put a little patch over one of their eyes, and it's, it's comfortable, and it's, it's fine. They don't mind it after, it's put on. They probably don't even notice it very much. But they're getting less, it would seem, they're getting less input than the babies that are seeing stereogram pictures because they have two eyes. However, maybe to offset that, they are actually getting a scene that's a real three-dimensional scene. It's, with real, plastic blocks in front of them, not just, image of plastic blocks, which is what the 2D picture baby group is going to get, and the stereogram picture baby is going to get. Of course, they're getting two different pictures, but this 3D, I'm sorry, this last group of infants, even though they're only able to use one eye, actually get a scene. Another thing I should say, just to kind of anticipate where we're going to be going with this, they're going to be able to move their little heads. Okay, that's not going to help the 2D and the stereogram babies because they're seeing two-dimensional images. But the baby with the eye patch that gets the scene in front of it is going to move its head. In other words, it's going to have motion parallax information available to it. And it is the only group of 3 babies that's going to have the motion parallax available to it. Motion parallax isn't available when you're looking just at a picture or a photograph, or even when you're getting stereogram pictures. Motion is not going to be available in that case. All right. So the question is, which of those 3 groups of babies is going to show the best, I guess, the best performance when it comes to size constancy? And you can test it the same way, with head turning and all that sort of stuff. Again, we're using cubes here, not mannequins, but you can, it's the same sort of thing. Will the cube be perceived as the same size at different distances, depending on the types of visual input they have? And so here's what you find. With the 2D pictures, they're not good at all. They do not show size constancy. In other words, they're not able to perceive depth very well at that point, at least, in order to show size constancy. So we're using size constancy as a way of kind of measuring depth in this case, measuring the sensitivity to the different dimensions, visual dimensions that might convey depth information. They don't show great high size constancy. The second group of babies, the ones that are seeing the stereogram pictures, okay, they do better. They show pretty good size constancy, all right? Not perfect, not as good as the kids in this original experiment, but they do well. The group that does the best, that shows the best performance in size constancy, are your pirate babies, okay? They show nearly perfect size constancy, despite only having access with a single eye, okay, little pirate patches on them for the time being, right? The fact that they're able to move around, the fact that they're able to turn their heads even just a little bit, right? At 2 weeks old, you're able to turn your head enough to kind of click off the switch, but you're not able to move your head like adults are, moving back and forth and all that sort of thing. You kind of move it a tiny bit like this. Just that much motion and seeing a real scene in front of them is enough for them to have the best size constancy. Again, suggesting that there's this primacy of motion for seeing depth perception. Again, motion parallax seems primary. It seems the most informative relative to these other types of visual input. Okay, motion parallax seems primary again. Okay, let's now jump forward in historical time and talk about this group I've been mentioning a few times throughout the quarter, including last class. This is the group from this Project Prakash that I've been talking about, which are a group of both teens and adults. A lot of this I'm going to be talking about is actually conducted with teenagers that had their vision enabled. I was going to say restored, but they never really had vision to begin with because these folks were born with congenital cataracts. Now, as I mentioned, cataract surgery is very simple. As I said, probably all going to have it at some point, or most of us are going to have it at some point. Your grandparents might have had it. It's not, I think it's all outpatient stuff, and it's local anesthesia and all that. But because of the fact that these are folks living in rural villages, they hadn't had access to it until, this group and this medical group in Project Prakash were able to, make this surgery technique much more transportable. So they went out to these rural villages and they, kind of restored sight or enabled sight to these people who had never seen before, which is wonderful. It really, it was, terrific. It really changed these people's lives. Here are some of the teenagers, and actually there's a couple of young kids there too, but the average age, I think, for the teenagers was about 13. And they also did adults as well. And, as you'll see, it really did change their lives, allowing them to see it for the first time. But it also, kind of allows for the addressing of this original Molyneux problem of, remember Molyneux, we talked about the fact that he was interested in if somebody all of a sudden had sight after, many, many years of being blind, but having access to other sorts of sensory information, would they be able to interpret the visual cues? Would they be able to interpret the visual input, I should say, more generally? And now you have a chance to test this. And, the teens and the adults were very willing to be subjects in these experiments. My gosh, they had their sight given to them for the first time in their lives. Yeah, sure, I'll be in your experiment for an hour. Let's learn something. Let's learn something about vision, about the brain, and I'm glad to help. And I'm thankful that I've got my vision now. Of course, they're going to be parts of this, and it was a collaborative experience for everybody: the physicians, the researchers who designed the experiments, and the individuals who had their sight restored, who were very interested in what could be learned about the brain from their experience. So here's what happens. So the question is, what can they perceive after their surgery? And just to kind of step back here, is it going to be something, is the pattern of results going to be consistent with what we've learned about infants and what I've just told you about infants? Now, most of these papers were started to be published in 2009, 2010, and there's been more and more of this published over the last 10 years since then. It's right now, I think it's about 200 to 300 individuals have had this cataract surgery. So, it's a nice number. Different people kind of have different sorts of experiences, but you see some very kind of systematic trends in what people can perceive after surgery. So very soon after surgery, after, the eyes heal, and they're able to start, to detect light and detect, forms and stuff like that through vision. They are able to, kind of see some things about figures, being like a circle or a square. They're able to, look at, say, a drawing of a circle and a drawing of a square, and able to then draw that themselves, right? And to say circle and square, they certainly know what a circle and square is by touch, and now they're able to say through vision, yes, I think I can see a circle and I can see a square. What they're not good with, though, and so they do have some problems, is if these objects are overlapping. What they'll say is, I see something that has a kind of curve to it, and I see something that has that's more angular, but they won't be, they'll interpret this as a separate shape. Rather than saying it's a circle kind of overlapping a square, they'll kind of interpret this as its own shape, which is, maybe they haven't, it would seem, acquired, the kind of whatever good continuation and closure sorts of abilities that the Gestalts talked about. So they're not able to do that at first, which maybe isn't surprising. And by the way, I should mention all these are tested with drawings or computer generated images on a surface, on paper, I believe, or a computer screen or something like that. So yeah, they're having a little trouble with that type of image. But what they find right off the bat, so here they might have trouble saying that this is a triangle, if the shape is shown in motion, they have very little trouble saying what shape it is. Okay, so in other words, what I could do is I could show these two things moving. So here's the circle, here's a square. If they're moving slowly past each other, or maybe kind of towards each other and past each other, they're able to say, even if the entire time they are overlapping, that one is a square and one is a circle. As soon as motion is allowed, things become much clearer to them, even after just having their vision restored. They might not say that this is a triangle. They might not be able to say if it's a triangle, if it's shown against all this kind of debris in the background. But as soon as you allow that triangle to start moving against this static debris, against this non-moving debris in the background, they'll say triangle. So motion, again, seems to enhance what's going on pretty well. Okay, cool. Then, oh, by the way, I forgot to mention this. So in both these cases, it is the objects that are shown moving. However, if you want to kind of put scenes in front of them, not pictures, not drawings, not images on a computer screen, but actual, things laid out on a table in front of people. If they are very still, they have trouble telling. But as soon as they start moving, guess what? They're able to tell what's going on much better. Still not perfect. Their vision's very fuzzy, but they're able to tell what's going on much better as long as either they are moving themselves or the objects are shown moving. The figures are shown moving in these two cases, right? All right. After 10 months, they can do this without much problem. Okay, they can look at these images and say, oh, it's a square and a circle and they're overlapping. They will not interpret this little piece here as a separate sort of thing, right? And they're able to say, oh, yeah, it's a triangle against, all these little lines there. They're able to do it without the motion, okay? And then the idea here is that these static cues, this kind of superposition cue, they're here too, I suppose, or good continuation cue or closure cue, seems to be kind of learned through their motion or the image's motion, the objects in the image's motion themselves. And so what's thought to happen is that they can now learn to use these pictorial cues, okay, from being kind of experiencing the pictorial cues through the types of information, the types of visual input that is much more relied upon, which seems to be either their motion or the object's motion. And then finally, after a few years, they're doing great. They're able to perceive these images without a problem. There's very few things you can present to them that they will not interpret like somebody who grew up with full vision, which in itself suggests something really interesting. When I was in college and graduate school, it was thought that if you didn't have, access to vision during a critical period of your kind of neural development, that you weren't going to be able to do vision very well. But this suggests something very different, right? And this is true not just of the teens that were in these experiments, but also the adults, that after experience, a few years of experience, even if you didn't have vision during the critical period of what they thought was, between 6 months and 2 years or whatever it is considered to be for other animals, it was thought that you wouldn't be able to interpret the visual world. Here it's showing now with this newer research, yes, even as an adult, if you've never had vision, it's given to you as an adult, you can interpret the visual world, and it can become your primary means of interacting with the world. Okay, which is really encouraging for other sorts of methods that are much more kind of technically challenging for restoring vision, right? The cataracts thing is very straightforward, but for people who have other types of blindness, when the technologies kind of develop to kind of provide vision to these individuals, will they be able to interpret the visual world? It seems yes, even if they've never done so until adulthood, which is nice. So this idea of an absolute critical period for the brain seems to now be questioned. right? That you can absolutely learn to perceive the visual world, even if you didn't have access as an infant like we used to think, which is very encouraging. So I think both in terms of that, but also in terms of the primacy of motion, that seemed like it was online very early on for these, patients after the surgery restored their vision, is pretty consistent with what we've seen with the infants, that motion seems primary. Suggesting, can I go through this last slide? Motion dimensions are primary. That's what I wanted to say. But can I go through this last slide? Do I have enough time to do this? Let me take a quick look. Okay, yes, I can. I'll do this. I'll just do this relatively quickly, but it's just summarizing what I say, and I should be able to do a question as well. All right. So it seems, based on the baby stuff and based on the Prakash stuff, that motion and perhaps binocular information seems to be primary. Maybe these things, well, we do believe that these things are true informational dimensions. They are lawfully related to, the scenario, that the kind of perceptual scenario that the person is in. And are they innate? Well, again, that's a very difficult question to address in any sort of thorough way. But they do seem to be online very, very early, versus the pictorial cues, which in a sense are dependent on the availability. They're not available very much. And they can have a number of different interpretations. And those might be the ones that have to be learned. Okay, we might not be able to use those, at least initially, as well as we can use the motion and stereopsis sort of dimensions, right? So when it comes to understanding the salience of cues versus information, it seems that what evolution kind of is depending on, as well as the infant and as well as the adults who have their vision restored, it really depends more on how those visual dimensions are tied to the environmental properties. If they are lawfully tied, like Gibson said, right, then that's what is going to be dependent on. It's going to be dependent more on how trustworthy, how kind of specificational those dimensions are, and not on what we might call the processing simplicity. And all I mean by this is what I said before in the previous slide, that it's a single image that provides pictorial cues, but that single image doesn't really provide very much reliable information. What provides reliable information is what's closely tied to the environment. Motion always means that you're going to induce this global flow, which is something Gibson said. Okay, cool. Let me spend our last minute just quickly doing our question. Oh yeah, I hear that California Adventure thing is great, Jenna. Thank you for mentioning that. All right. Let's do our last question here. And this is just infant depth perception. According to the infant research discussing class, which seems to be the most primary information for allowing babies to perceive depth? There you go. Is it linear perspective, relative size, binocular disparity, motion parallax? Yeah, I said this just 100 times in the last minute. Okay, I want to make sure that you all have this in your notes, so I will just give it another 10 seconds, and it looks like pretty much everyone's doing this, right? Okay, terrific. The correct answer is, in fact, D. They don't seem to be able to use relative size, or at least rely upon it very well. Binocular disparity is not bad, right? But by far, what seems to be most relied upon is motion parallax, which is D. Linear perspective is another pictorial cue that actually isn't used very much. But based on what we said, based on our discussion, motion parallax is the answer, D. Oh, sorry, I didn't share my results. There you go, D. There you go, take a picture of that. I apologize. Okay, everybody, have a good weekend, and I will see you on Tuesday.